Hello, this is Sean from Beyond Kinematics. We have prepared a video to demonstrate how the use of simulations and digital twins can provide tremendous value for real-time code development. In a typical machine commissioning lifecycle, control software development is very dependent on physical hardware, mechanical assembly, electrical wiring, and lead times of physical components. Components that need to be ordered, received, and then installed and integrated into the overall system. Unfortunately, with this approach, delays in the procurement, design, and assembly process translate into a highly shortened controls development timeline. Rather than a polished, robust machine, large amounts of technical debt are introduced into the equipment. If a project deadline is to be met and all other facets of the project are running behind, the controls development time gets shortened tremendously. What is arguably the most important process of machine development is relegated to the absolute shortest development time. At Beyond Kinematics, we advocate for a different approach. Imagine being able to develop your code offline on a CAD-accurate representation of your system. Motion control, physics, vision, and sensors can all be accurately simulated and interfaced with a real-time controller in this environment. With this approach, a robust and well-optimized machine can be realized and at a much faster pace. We believe this is the future of machine development. Felipe will demonstrate more about this approach in the following video.
Hi, this is Felipe with Beyond Kinematics. I would like to present a glimpse of the simulation, the HMI, and the PLC projects. Here in Unity, I have a scalar robot responsible for picking up products from the left conveyor using a vacuum cup and placing them into the boxes on the right conveyor. The conveyor's operation is controlled by two proximity sensors. Check this out. The sensors emit a light beam that triggers a Boolean signal on the PLC when the beam is interrupted. The right conveyor will run until the proximity sensor detects the presence of a product. Once the conveyor comes to a complete stop, the product will be positioned within the field of view of this camera. The image captured by the camera will then be processed by TwinCat Vision, which will decode the QR code and extract a string containing the product lot, manufacturing date, and serial number. Let's have a look at the HMI. The home page presents some high-level information about the process. Like the vision results, the green rectangle represents the contour of the detected QR code. The decoded string is printed on top and the processing time on the bottom of the image. Less than 1 millisecond. This is only possible because the vision task runs inside the PLC, so there's no waste of time on communicating with an external vision server. I also have an implementation of a PackML state machine, and its current state is shown here. Note that upon pausing the process, the machine will transition to the suspending state until the robot is at rest. At that point, the state machine will finish its transition to the suspended state. Now, I can go to the manual mode and jog the robot. Upon pressing play again, my process will resume from where it stopped. Finally, an event grid shows all the history of the messages and alarms. Messages are stateless and alarms can be cleared or acknowledged. Upon clicking on an entry, the details of the event, such as the description, data and time of occurrence, and source, are shown, making it easy to understand what could be preventing this process from functioning. Let's demonstrate how to leverage this digital twin to do offline PLC code development. I want to modify the control logic to handle a scenario where the camera cannot read the QR code. If that happens, the robot won't pick the product and the conveyor will index once. Eventually, the ignored product will fall over a reject bin placed by the end of the conveyor. To test that, we can change the orientation of the product so the camera can't see the QR code. Let's dive in the PLC code and do some changes to address that. The method execute in the FB pick-and-place function block orchestrates the sequence during operation. It has a state called read QR code, which calls the vision task. We need to create another transition which will take the process to a state where the left conveyor can be indexed once. This transition will happen if the decoded string is null. First, let's add an enumeration for this new state, indexconv1. Next, a new transition needs to be created. If the vision task was requested, and it is over, and the decoded string is null, then we go to the state indexconv1. I will also change the first transition to include and decoded string is different than null. In the new state, the conveyor will run until the part is no longer sensed. And then a transition to the get ready state will be triggered. Then the vision task needs to be reset. And finally, we can issue a warning message saying that the QR code could not be decoded. Now we test it. And it works. The sequence was changed to ignore products that the camera could not read, and a timestamped message is available in the system log. We have demonstrated the utilization of a digital twin for offline validation of PLC code. But this isn't all. This pipeline can be used during the entire life cycle of a machine. Here are the key advantages and applications for it. Enhanced sales effort. By offering clients a realistic visualization, the digital twin allows potential customers to better understand and visualize the machine capabilities. Improved decision making. During the proof of concept stage, the digital twin assists system architects in making informed decisions. Its simulation capabilities provide valuable insights and enable architects to optimize various aspects of the machine design. Streamlined development. The digital twin significantly reduces development time for PLC code, leading to higher efficiency and improved quality of the end product. With fewer bugs and enhanced error handling, it ensures a smoother functioning system. Training platform. After commissioning, the digital twin can serve as a training platform, facilitating the education of the service team. This reduces downtime, providing added value to the customer. Efficient change management. The digital twin is instrumental in managing changes to the machine processes while minimizing downtime required for implementation. It enables seamless integration of modifications and optimizations, ensuring smooth transitions and operational continuity. At Beyond Kinematics, our expertise lies in digital twin development services. However, we are also well equipped to cater to your needs in PLC, vision, robotics, HMI, and data acquisition. Thanks for watching this video.